Chemist's Corner presents Fun with Liquid Nitrogen. We're going to put some liquid nitrogen in a water bottle. We're going to put some more liquid nitrogen into a Coke bottle. And we're even going to put a balloon into liquid nitrogen and see how much of that balloon I can stuff into that Dewar flask. Stay tuned. Hello, Chemist's Corner. Today, we're going to play around with a little bit of liquid nitrogen. Now, liquid nitrogen is insanely cold, minus 196 degrees Celsius, which works out to be 77 degrees Kelvin. When you compare that to room temperature of about 22 degrees Celsius, or 295 kelvins, there's over 200 degrees difference. I have some liquid nitrogen in my Dewar flask here, and a Dewar flask is simply a flask that is silvered on the inside, has a glass layer, a vacuum, and then a glass layer, which helps to insulate it against that almost 220 degree difference. The liquid nitrogen in here boils instantly when it hits the table. First, I would like to just add some liquid nitrogen to a beaker of distilled water. I've got about a liter of water there, just a little less. And if I add a little bit of liquid nitrogen, it boils over like a witch's cauldron. Now, what you are seeing is not actually the liquid nitrogen. What you are seeing is the water vapor condensing in the air, and of course, cold air sinks, and so it then flows down over the table. If we try that same procedure with a smaller container with less water and a little bit of universal indicator, we'll see a little bit more color. Now, when I add the liquid nitrogen to it, you will see that, well, it does the same thing as it did in the other container. The color does not change. And since the color does not change, that tells you liquid nitrogen is neither acidic nor basic. It doesn't really change the universal indicator that much. It is neutral. Let's refill my liquid nitrogen in my Dewar flask. The air inside this balloon is currently at room temperature at 295 degrees Kelvin. But when I put it into my liquid nitrogen, it cools down very quickly and shrinks according to Charles' law. And according to Charles' law, the volume and temperature are directly proportional. So as the temperature falls, so does the volume of the air in my balloon. And as you can see, my entire balloon fits quite nicely into my Dewar flask. When I pull it out, my balloon is currently at 77 degrees Kelvin, and if we warm it up carefully, it will expand back up to its original volume, assuming it doesn't pop. Things that are normally flexible at room temperature can become very, very brittle when they become cold, such as a rubber hose. Very flexible at room temperature. We can twist it all over the place. But when I put it into my liquid nitrogen and leave it there for long enough, it becomes quite brittle. You can see my balloon is now flexible again. It will take a little while for my hose to cool down, but when it freezes, and freezes hard, it will be hard. It will not be flexible anymore. When I pull that out, it can now shatter on the second try. Even things such as jelly candies, very flexible when they're at room temperature. But when I put them into liquid nitrogen and cool them down, they will shatter with just a single shot of a hammer. Now that my jelly candy is nice and cold, and it shatters immediately. Things that contain a lot of water, like tomatoes, when we freeze them in liquid nitrogen, they too become extremely brittle. And I'll just put a couple of tomatoes in there with my styrofoam cup, and we'll see what happens. This time I'm going to put them in a Ziploc bag because I don't want to get shattered tomato all over myself. It will take a few seconds for the tomatoes to freeze all the way through. Even at 77 degrees, it does take time to freeze. When it stops boiling, I know they're ready to be shattered. While we are waiting for the tomatoes to freeze nice and solid, let's watch that rubber hose again in slow motion. Now, it's still a rubber hose. It hasn't changed its chemical consistency. There was no chemical reaction, but now it's brittle. Have you ever seen rubber shatter like that before? Well, it's still rubber, but it's not flexible rubber because of the extreme cold. Okay, I think my tomatoes are ready. Let's pour off the liquid nitrogen that we don't need. And here's what my tomatoes look like. I'm simply going to put these into my Ziploc bag so that I don't make a mess on my counter. And hit them with a hammer. And they shatter like they were glass. Even a common flower, when frozen, will shatter very, very easily. We'll put it in the liquid nitrogen and give it a few moments to freeze up. And we'll clean up this area. Let's watch the flower being shattered in slow motion. The once flexible flower, like the rubber hose, is not so flexible anymore. Now that the flower is off the stem, even the stem can be shattered very easily, but is flexible when it's warm, shatters when it's cold. Now, the expansion from minus 196 to plus 22 is most evident when you do it in a sealed container. So I've got 3 sealed containers that I'm going to put liquid nitrogen into. Just a water bottle, a Coke bottle, and a 2-liter soft drink bottle. You'll see the difference. Now, before I blow up the 3 containers, and don't worry, it will happen, here is another quick demonstration of a gas law. This time, Boyle's law, which describes the increase in the volume of gases as pressure increases. The liquid nitrogen that I just poured into my test tube is boiling, which results in many more gas particles in my closed system. This in turn increases the pressure, causing my balloon to expand. Eventually, the pressurized expansion of the balloon will cause the balloon to fail. Let's watch that again in slow motion. Okay, it's time to blow up some bottles. My first victim is a light plastic bottle used to contain drinking water. I'm putting a little water in the bottom to increase the visibility of the fumes given off after I add the liquid nitrogen. Once again, it is the condensing water vapor that you are seeing, not gaseous nitrogen, which of course is invisible. This kind of bottle is not designed to withstand large pressures, so when the pressure does increase, it will rupture almost immediately. And after our explosion, this is all that remains of my former bottle. A little plastic bottom and some fumes. Let's watch that rupture again in slow motion. After I fill up the bottle with liquid nitrogen, look at the pattern the fumes make. This is a very turbulent flow. And after I seal it, watch the direction that the fragments of the bottle go. Keep your eye on the left. Did you notice? The lid didn't fly off. The entire bottle ruptured instead. Round number 2 uses a slightly more rigid plastic bottle. You may recognize the shape. It's a Coke bottle. Once again, I'm starting with the addition of a small amount of water in the Coke bottle, just to increase the dramatic effect. And just ignore the splashes on the backdrop from my first explosion. As I add the liquid nitrogen, remember that Coke is a fluid that is bottled under pressure. So this plastic bottle was designed to withstand much higher pressures than the water bottle was previously. Again, what you are seeing is water vapor rapidly condensing in the presence of the very cold liquid nitrogen. Once the bottle is sealed, the pressure inside builds rapidly and directly proportionally to the number of moles of gas as my liquid boils. This increase in the number of particles in a closed, rigid container increases the pressure according to the ideal gas law, and the higher pressure eventually ruptures the bottle. Notice in the lower right, a piece of the bottle embedded in my backdrop, and to the left, the rest of the bottle blew right through my backdrop. One more time, this time in slow motion. Even in slow motion, that's a pretty fast reaction. Round number 3 uses a 2-liter bottle that, like the Coke bottle before, was designed to withstand significant pressure from a carbonated beverage. Again, I start with a little water, followed by the liquid nitrogen. The water cools rapidly, and the once flexible container cools down significantly and becomes more rigid. Now sealed, we get to hear significant crinkling noises as the gases within the bottle attempt to expand according to Boyle's law, but are resisted by the container as it becomes more and more rigid. The contents try unsuccessfully to maintain room temperature, but the pressure continues to build. The gases want to increase the volume, as Boyle's law would suggest. Of course, this is resisted by the size of the container until ultimately the pressure wins and ruptures the bottle catastrophically. The resulting shock wave absolutely destroyed my backdrop. And what looks like snow in the lab is really just dust coming down from the ceiling, dislodged by that explosive shock wave. If you enjoyed this video on liquid nitrogen and found it either entertaining or educational or a little bit of both, please indicate so by liking, make a comment below. And if you've not done so yet already, please become a subscriber and tell others about Chemist's Corner. See you again with more infotainment or just plain fun in the lab in Chemist's Corner.